Today I'm going to solve the sixth problem of Gauss's law. So it's a uniform charge density, spherical charge density, so this is question number 6. And it's a sphere. So it's a sphere with non-uniform charge density, rho equal to a constant divided by r plus c, where a and c are both positive constants, and it's equal to 0 when r is bigger than or equal to capital R. So it's a sphere with a radius of capital R basically, and the charge is non-uniform. Of course it's non-conducting, they're not allowed to just move. Okay, so, and the question is the following. It has actually 4 parts. First part is the following. Calculate total charge, Qt, as a function of capital R. It's going to depend on capital R, A, and C, and constants. So, how do we do it? So, let's draw the figure first. So, this is a sphere of a radius of capital R, right? The sphere is composed of all these spherical shells, right? With an inner radius of R and an outer radius of R plus dr, where the thickness of this spherical shell is dr. So what you can do is you can think this sphere as a composition of all these spherical shells from 0 to capital R. And if you just add them up, then you get the whole sphere, right? So as you know, this is a non-uniform case. As you know, if it had been a uniform sphere or uniform object in 3D, what we would do is we would say, okay, Q total is basically rho times V, the total volume, right? But for non-uniform, we can't use this simple formula, right? And the reason is because this rho changes. Which rho am I going to take? It depends on the radial distance that we choose. And that's why we can't do that. Instead of doing that, we take a small portion of this three-dimensional object. We call it dq. It's an infinitely small part. And that's equal to rho times dv. And now the reason why we can put this rho here, it depends on r, yeah, but for the small infinitesimal volume, we can approximate it to be almost constant, because this volume is infinitely small. And then what we do is, and for this case, that volume is this guy, right? So it is this volume which is between these two spheres, okay? And for that, rho is constant because this is infinitely small volume. And then what we do is we add all these infinitely small volumes to get the whole thing, right? So that is why when we integrate the whole thing, we get the total charge Q. Okay, so this is uniform versus non-uniform. If it had been uniform, it's very easy. You just multiply rho by the volume. But for this case, it's a little bit more involved. Okay, so this is a spherical distribution, right? This is a sphere. And I'm going to find out the infinitesimal volume, which is this blue guy. And it says the volume between two spheres. So what you can do is you can subtract the inner sphere from the outer sphere. Inner sphere being the radius of small r, and the outer sphere is r plus dr. You can do that. Or you can simply take the d volume is the volume of a sphere, 4 pi r cube. This is d of v. And if you do it, the derivative hits here, and that's going to give you 3r squared dr, and that recancels this guy, and you get 4 pi r squared dr, okay? And again, you can think this like, take a sphere, inner radius is r, outer radius is r plus dr, cut it, open it up, and the surface, it's going to look like a surface and a thickness of dr, where the surface is equal to 4 pi r squared, and the thickness is dr. So now rho, right? And rho is given, the form of rho is given here. Let me write it down. So integral of rho dv, where rho is a divided by r plus c, right? So this is rho. And I'm going to multiply that by dv, which is 4 pi r squared dr, right? So this is rho times dv. And q total is equal to that, where r changes from 0 to capital R. I'm adding all these spherical shells starting from 0 up until capital R, where capital R is the radius of the sphere. Okay, so I guess the first step is take the constants out of the integral. So I have 4 pi times a. That's constant. And now I have the following integral. I have dr times r squared, that divided by r plus c, from 0 to capital R. Additional video, how to evaluate this integral. And there's actually a nice way to do that. And you might, think that there are easier ways. And you can leave that as comment in the video. But I will show you how to do this, evaluate this integral. Here, I'm not going to do that. I'm just going to write down the answer for that. So it's 4 pi times capital A. That's the term. And this integral actually gives us the following. So it has r squared over 2 minus r times c plus we have c squared logarithm of r plus c. So that's basically what you get if you evaluate this integral. Again, I'm going to show you how to get that, okay? And again, we evaluate this integral from 0 to capital R. And now I'm ready to write down Q total. So this is Q total. Okay. And I'm going to put the upper part and lower part of the limit of this integral, and let me write it maybe here. Yeah, so Q total is equal to, so I have this term again, 4 pi times A. If you put the upper part, that's going to be r squared over 2. So that's going to be r squared over 2 minus, now capital R C. And when you put the lower limit, this and that guy goes away. It only contributes to this one, right? So that's why the upper one is going to give you c squared logarithm times capital R plus c. So I'm just putting r equal to capital R. Now the lower limit, this gives 0, that gives 0. The only non-zero is the other one. So I'm subtracting the lower limit, c squared logarithm. And this time, as you can see, when r is equal to 0, it's just logarithm of c. Okay? So I get this expression. These are okay. And you have here c squared logarithm of something, c squared minus c squared logarithm of another thing. And you know that subtracting two logarithms is the same as taking a logarithm and dividing the things inside. So therefore, the final answer, so let me write it here in here. So the final thing for Q total is going to be equal to 4 pi A, okay? And here I have, these guys don't change, so that's r squared divided by 2 minus rc plus in c squared parentheses, I'm going to have a logarithm of r over c divided by c, which is, let me write it here, r over c divided by c is nothing but r over c plus 1, right? C divided by c. And I'm going to write it like 1 plus r over c in here. So that's basically Q total, okay? So that's only the first part of the question. So I told you that this is a little bit involved, but it's okay. The second part of the question is basically the following. It's a nice limit that actually we are asked to take, and that's this. It's the following: for the limit when c over r is much greater than 1, or another way to say that is when c is much bigger than r. Okay, this constant c is much bigger than r. Again, do the same calculation. What is Q total? So make that approximation and calculate it again. And you might just give it exactly the same thing, but it's not asking that. You can even assume that this is like infinity. when it's like infinitely big, then what would this expression look like? Okay, so we can of course write the same thing, right? So let me write it if you like. So that's going to be 4 pi a, and I can take r squared parentheses here, r squared out of this, and that's going to be like 1 over 2 coming from here, and from here that's going to be c over r, right? I'm taking r squared parentheses, and this guy is going to give me c squared over r squared with a logarithm term of 1 plus r over c. Okay, so let me even close the parentheses here. And now you see what the problem is. So this is just a constant. Now c over r is a big number. That's going to dominate that number. And it looks like it's, okay, this is negative, but how can charge be negative? It was always positive, right? But now the problem here, you see this when c is much bigger than r, that's going to be like logarithm of 1. It looks like 0, but it's not 0. There's a c squared r squared in front of that, and that's a big number. So that big number is going to dominate that. And how are we going to do that? How can we express this in terms of c and r and all that? And actually, I'm going to do that in, and again, another additional video, how to do that mathematically. Again, another video. How to make an approximation for this logarithm of 1 plus a small number. But here we're not going to do that because you see, like, question is asking us, it's not just any limit, it's this limit. And why is it asking that limit? Let's remember the definition of our non-uniform charge density. That was A divided by R plus C. So you see, when C is much bigger than R, and remember that R can take values between 0 and capital R, right? But for any value of R, C is always much bigger than R. So what that means is this actually, for that approximation, when C is much bigger than R, this simply becomes A over C because you can just forget about R. But what does that mean? It means like A is constant, C is constant. That means rho is simply a constant. So the whole thing becomes a uniform charge distribution, becomes uniform because this is constant, right? Okay, all of this complication that arises because of the non-uniformity goes away. And that's why they have a uniform charge density, and for that, calculating Q total is extremely easy, right? So again, you just multiply rho by V, and in this case, rho is constant, so therefore, let me write it maybe here, yeah, for the second part. Q total will simply be rho, in this case, it's going to be A over C, multiplied by the volume, which is volume of the whole thing, which is 4 over 3 pi times r cubed. So that is indeed what you get for part B. And again, in another video, I'm going to show you that making some mathematical approximations like 1 plus small argument, and if you expand it in terms of the argument, I actually am going to show you that this is going to give you the same thing, but no need for now. Okay, so the next part is now related to Gauss's law. Okay, part C, it's asking us, probably you guessed, the electric field. What is the electric field for the case when R is smaller than capital R? Okay, so you remember what the Gauss's law told us. It's the flux is equal to EdA integral, right, of a Gaussian surface, closed Gaussian surface, and that's equal to Q enclosed divided by epsilon 0. And here, since this is completely a spherically symmetric object, the best Gaussian surface is again a sphere. And for the sphere, you can just, every point on the sphere is exactly the same, no dependence on the dA, so you can take E out of the integral. So this is a nice Gaussian surface, a sphere. So that's why this becomes E goes out of the integral, and you just have dA. And this is nothing but 4 pi times the radius square of the Gaussian surface. In this case, the Gaussian surface is this guy, right? And that's equal to Q enclosed divided by epsilon 0. And therefore, the magnitude of E, and the direction is radial direction, radially outward, because it's positively charged. So doing that, E becomes Q enclosed divided by 4 pi epsilon 0 times r squared. And the direction is r hat. But the nice thing about this thing is I already know what Q enclosed is, because here the integral is for any r, right? Not necessarily a capital R. You can just take Q for the enclosed region from 0 to small r. And this is exactly the expression that you want. So I already calculated that. I'm just going to take this, so let me give a number to this equation, equation number 1, and put that Q in this equation for the enclosed Gaussian surface, where you just replace capital R by small r, right? And so electric field becomes, E has the following shape. So you have r hat, and now we have 1 over 4 pi epsilon 0 times r squared. And inside this, I have this following expression, 4 pi a. And remember what I did, I think at this step, yeah, I took, I think here, yeah. At this step, I took r squared out of the integral. It's a good idea to do that, because then, or in here, if you take r squared out of the integral, then it's going to cancel that r squared. So I'm taking that out, r squared. And inside, I have now 1 over 2 minus c over r plus c squared over r squared with that logarithm term. Okay, I'm going to put the arguments inside the logarithm here after I do this cancellation. I get rid of 4 pi's and r squares. Now it's much simpler, as you can see. So the expression for E, when r is smaller than r, is going to be r hat. And on the numerator, I get a over epsilon 0. And I'm going to multiply that with this parentheses. 1 over 2 minus c over r plus c squared over r squared with this logarithm term. Now I'm going to put the argument in. And I'm going to even box it. Okay, so this is the whole expression when r is smaller than r. And finally, what is it when r is greater than r, right? So that's the final part. So that's D. Calculate the electric field for the case of r greater than r. Again, the same expression, everything is same, this did not change. Now the Gaussian surface is this thing, right? So we're interested at a point which is r greater than capital R. Now this is the Gaussian surface, and therefore this area here, 4 pi epsilon 0 r squared, is exactly the same. That didn't change. The only thing that changes is now it's going to be r hat times q enclosed. And here, remember that q enclosed is nothing but the total charge, right? It's just the total charge of this non-uniform charge distribution. But I already have the answer for that, right? But before that, let me write the expression for you. So that's going to be E is equal to, okay, so it's equal to r hat q total now, 4 pi epsilon 0 r squared. Now let's put q total here, and that will be the final answer for us. So I'm going to write it here, maybe another place. Oh yeah, here. E will have the following form, r hat. Now q total have 4 pi a, and again I'm going to take, since it's total, capital R square out of it, and yeah, 4 pi a times capital R squared times 1 over 2 minus c over capital R plus c squared over capital R squared times this logarithm term. And all of that are going to be divided by this, right? 4 pi epsilon 0 times small r squared. Now there are some cancellations. 4 pi's go away. But now this r squared does not, they don't cancel each other, because this is capital R and this is small r, and the rest is here. So let me write down the final answer in here. E, this is for r greater than r, is going to be r hat times now a divided by epsilon 0 r squared divided by small r squared. Inside the parentheses, I get 1 over 2 minus c over capital R plus c squared over r squared times this logarithm of 1 plus r, capital R divided by c. So sorry about that. Too many equations, but I'm going to box it so that we can clearly see. Okay, so this is the final expression for part D.